Effect size, right? Statistically, they did better. They did better, that the sleep aids did better than placebos, all right? But the question is, if you increase total sleep time by 11.4 minutes, what kind of effect size is that? Is that something you would want to try? Especially if you're weighing it against either the cost of the medication or side effects or something like that. So this gets back to the whole idea of significance versus effect size. Significance, yes, the sleep aids did better than placebos, but effect size, is it worth it? Is it worth it? And they make the comment in here that actually the older sleep drugs like Halcyon and Restoril tended to work somewhat better and cost 30 to 50 cents a pill. Okay, so that's an interesting little thing. The other thing that I just found kind of interesting was in terms of how do these sleep aids work? I mean, people are not getting that much more sleep, but they report being satisfied with the drugs. So what's going on? So an interesting thing was most sleeping pills work on the same brain receptors as drugs to treat anxiety. By reducing anxiety, the pills may make people worry less about not going to sleep, so they feel better. Okay, that was one possibility. Another theory about the discrepancy between measured sleep and perceived sleep involves something called anterograde amnesia. That is, well, under the influence of most sleep medications, people have trouble forming memories. When they wake up, they may simply forget they had trouble sleeping. So it's just interesting, right? This is why I bring this stuff to your attention, because I want you to weigh the cost and benefits of certain things and understand there are questions that you can ask. Yeah?
Isn't anterograde amnesia the inability to form memories, like moving forward? I was taught that retrograde is when you can't remember things.
That could be. I don't know. They reported as anterograde, but you know, maybe they had a different understanding of what it meant for this. I'm not sure. Okay, so yeah, so again, I'm just bringing it to your attention because, again, this is what we've been talking about between the difference between significance and effect size and the cost-benefit analysis that goes into whether you want to implement something, whether you want to take a drug, whether you want to implement a particular program. I mean, one of the things that I would like to see that I never see information on is we have all these political conversations about healthcare, right? Healthcare, do we do this, do we do that? Do we, you know, public option, no public option. I'd love to see data. Does this work? Now, you can see some stuff that comes over. I was reading things about Great Britain's healthcare system. So that has some information. But the question is, like, does it apply here? It's very difficult. It's very messy to kind of look at these things, but I think it's worthwhile. Anyway, so that's effect size and significance. Okay? Now we're going to move on in chapters 9 and 10 to something else. Okay? Chapter 9, and this should give you a relief after chapter 8. Chapter 9 is quite easy, actually. Chapter 9 is what we call correlation. Correlation. What's correlation? The relationship between two variables. And chapters 9 and 10 usually go together because chapter 9 is about the strength of the relationship between the two variables. That's correlation. And chapter 10 is about using one variable to predict values on the other variable. That's called regression. Regression. So correlation and regression are taught together because, again, one is talking about the strength of the relationship, and the other is using that strength as a predictor for prediction purposes. Okay, we're only going to get through correlation today, but like I said, it's a pretty simple topic, right? Because we're talking about the relationship between two variables. So let's start out with an idea. What is a perfect correlation look like? A perfect correlation. If two variables are perfectly correlated, what does that mean? Well, let's think of some examples. If everybody in the class got the same grade on their final as on their midterm, those scores would be perfectly correlated. It would be a perfect relationship. Essentially, when we're talking about relationship, we're talking about if I have information about one variable, does it give me information about the other variable? That's really what we're talking about. So if you have the same score on midterm and final, then yeah, if I know your midterm grade, I'm going to know your final grade. It gives me perfect information. Okay. What if everybody got 10 points higher on the final than on their midterm? You know what? The scores would still be perfectly correlated. The scores would still be perfectly correlated. Why? Because when we're measuring correlation, it's not the absolute value of the score that we're interested in. What we're interested in is the locations of scores in the two distributions. Locations of the scores. Now, when we talk about location of scores, you guys have all heard this already. When I talk about a location of a score in a distribution, what was that? Z-scores, right? Z-scores told me about the location of a score in a distribution. So one way to think about a perfect correlation is that if everybody's scores, let's say, again, midterm and final, if I put everybody's scores into Z-scores, then if the midterm and final are perfectly correlated, that means that the Z-scores you got on the midterm are exactly the same as the Z-scores you got on the final. Okay? Again, because they're measures of location. It's not that the numbers are the same. It's that the place in the location of the distribution is the same. However many standard deviations above or below the mean you fell. Okay? All right. So let's take a look. How do we measure correlation? We measure correlation with something called a correlation coefficient. And on the bottom here, this is actually a formula for correlation. We're not going to use this because, look at it for a moment. It uses the Z-scores, which is useful for us to see that that's right. It's talking about how the Z-scores match up. However, we don't usually use this formula because we'd have to transform all our scores into Z-scores before we did it. So nobody really does this. This little letter R, that is our correlation coefficient. More specifically, it's called the Pearson product moment correlation coefficient, which is a big name. The Pearson product moment correlation coefficient, mostly people call it a Pearson's R. A Pearson's R. All right, I think product moment came from an engineering term when it was originally developed. So we refer to it as a Pearson's R. So that's the correlation coefficient that we're going to be using to assess the degree to which two variables are related. Okay? So let's talk about some characteristics of the Pearson's correlation coefficient. First of all, it can only range from -1 to +1. It only ranges from -1 to +1. It can't be lower or higher, or more extreme if it's easier for you to think of, than -1 or +1. The closer it gets to 0, the weaker the relationship. The weaker the relationship. The closer it gets to either -1 or +1, the stronger the relationship. So just because you have a negative number doesn't mean that it's a weak relationship. Okay? It's just as closer as the numbers get to either -1 or +1, that's strong. The closer to 0, that's weak. Now, what does the negative and positive tell you? Those tell you the direction of the relationship. So a positive correlation is sometimes called a direct correlation. That's another name for it, a direct correlation. And that means that the variables are moving in the same direction. That is, as one is increasing, the other is increasing. Or as one is decreasing, the other is also decreasing. That's a positive correlation. Okay? An example of that, in theory, the number of hours you study for an exam and how well you do on an exam. In theory, the more you study, the better you do. And I say in theory because I know some people tell me otherwise. Okay? So what is the negative? A negative correlation, sometimes called an inverse correlation, means that the values go in opposite directions. That is, as one variable is increasing, the other is decreasing. So an example of that might be the number of years you own a car and its value, right? Because the more you own it, the value goes down. Okay? So those are negative and positive correlations. So the sign tells you the direction of the correlation, and the number tells you the magnitude, the strength of the relationship. All right? Now, as we've mentioned before, about 100 times at this point, correlation does not imply causation. Okay, here's a little article to wake you up. This was from last February, so it's a little more recent than the other one. And this has to do with a guy who set up two websites. One of them is called Books That Make You Dumb, and the other is Music That Makes You Dumb. And he decided that he was going to look at the correlation between the type of music or the type of books that people read or listened to and the music that they listened to. And their SAT scores, okay? So for example, the favorite musician of the smartest students was Beethoven with an average SAT score of 1371. Also on the smart end of the scale were Sufjan Stevens, Counting Crows, and Radiohead. And sadly for Lil Wayne, enjoying his music was associated with being the dumbest with an average SAT score of 889. Okay? All right. On the book front, Lolita was a favorite tome of the brightest students, which, well, just not going to touch that one, okay? With an average SAT score of 1317. The lowest scoring students liked the erotica author Zane with an average score of 980. And strangely, the students who listed their favorite book as the Bible were smarter than those who said it was the Holy Bible. Okay? But I love, this is my favorite. Ironically, students who wrote, I don't read in the space for favorite books were only slots 14 from the bottom in terms of SAT scores, meaning that there were 13 other favorite books that theoretically made students dumber than not reading books at all. That was my favorite. Okay? But again, right, this is just, it's amusing because does it mean that that music makes you dumb, right? Or, I mean, aside from the fact that, like, how representative do you think SAT scores are of your intelligence to begin with, right? So it's all of these things that go in there. But it's just, again, it goes back to the correlation and causation idea. And it was just an amusing thing. By the way, after his stuff came out, his websites crashed because of the traffic on there. Everybody was interested. But yeah, I mean, the truth is, you can do correlations between anything. You can find numbers. But I like that. Okay. So let's talk some more. All right. What happens if we put numbers through a linear transformation? Right? A linear transformation, like if we put them into z-scores, is a linear transformation. But any other kind of linear transformation, adding, subtracting, multiplying, dividing by a constant. If I have one set of scores and I put them through a linear transformation, those scores will be perfectly correlated. They'll be perfectly correlated, right? Because a linear transformation doesn't change the location of your scores in a distribution. A really simple way of thinking about it, a real simple example, is if you imagine I took everybody's height in the room in inches, and then I transformed them into centimeters. The correlation between inches and centimeters would be perfect, because it's just a simple linear transformation. Okay? So, let's talk about pictorially, graph-wise. What do these look like? What do correlations look like? Well, here's an example of perfect correlations. The top one is a perfect positive correlation, and the bottom is a perfect negative correlation. And again, if you think of correlation, let's use the amount of information you have from one variable to think about the other variable, then you can have some understanding, right? Like if I know what my x value is, I'll know exactly what my y value is, because all of these points, they fall on a straight line. And again, as x is increasing here, y is increasing, so the points are all on a straight line. Right? Down here, this is a negative correlation. As x is increasing, y is decreasing. Now, let's look at not perfect correlations for a moment. All right, these are strong correlations. I want you to think, this is how you could look at a correlation on a graph, right? First of all, these are called scatter plots, and you put one variable on the x-axis, the other variable on the y-axis, and you graph those pairs of scores, okay? So one way to think about this is if you were to draw, and we talk about drawing an envelope around the points. As we draw an envelope around the points, the more elongated oval that is, the better a predictor it is, the stronger your correlation is. The more circular, the weaker. So for example, let me draw it up here. Let's say the points look like this. Okay? What that means is that as x is increasing, it tells me nothing systematic about y. I don't know what y is doing. Sometimes it goes up, sometimes it goes down. It doesn't give me any information, right? Here, as x is increasing, I see that y in general is increasing as well. But up here, as x is increasing, I don't know what's going on with y, right? There's nothing systematic going on there. So the more circular, the weaker your correlation. So this might actually be a correlation of 0. Whereas this is a correlation of 0.83. And you can see, right, I said the more elongated it gets, right, or the more oval it gets. So until ultimately, right, all the points fall exactly on a line. Now, just to jump ahead for a moment, in chapter 10, this is essentially what we're doing, okay? If I graph my variables on a scatter plot, my x on the x-axis, the y on the y-axis, and I get this scatter plot of dots, in regression what we're going to do is find the best line that goes through that plot, okay? The equation of that line will be a prediction rule. So if I know my x, I can predict what's going on in y. That's all that's going on. I have these points, and I put a line through it. That's what regression is going to be. Okay? So here we're just talking about the strength of the relationship. All right? And this is, again, this would be a negative correlation. Okay. Now, one thing I want to mention is that Pearson's R, the correlation coefficient I'm showing you now, only applies for a linear relationship. A linear relationship. That is a straight line relationship. Sometimes you'll hear it said that the underlying data structure is linear. That is, a straight line is the best description of what's going on. So in these cases, I could put straight lines through it, and that would be just fine. But what if I had something that looked like this? All right? That's called a curvilinear relationship. Curvilinear, right? There's a curve in there. If I put a straight line through it, well, first of all, the best straight line would probably be like this, and it would go through like that, and it would be useless. It would be useless. There is a strong relationship between these two variables, but it's not described by a straight line. So if you used a linear measure, such as Pearson's R, to calculate the degree of relationship between these two variables, very likely it would tell you there's almost no relationship there. That's because it's not linear. All right? You would use something else. You guys aren't going to learn that. I'm not going to teach that to you. But you would just use some kind of different measure to understand that relationship. Now that relationship is an example, this curvilinear, this little curve here, is a relationship with something called the Yerkes-Dodson law. Anyone ever hear of the Yerkes-Dodson law? It has to do with performance and anxiety. Okay? These researchers, Yerkes and Dodson, thought maybe there's this relationship between anxiety and performance. And they found that, yeah, what happens, they were looking at it first in athletes. What happens is if you have too little stress, too little anxiety, you don't necessarily perform very well. That's the bottom of this curve. And if you have too much stress, you also don't perform very well. But there's a sort of optimum amount of stress for performance. And I don't know about you guys, I found that in school. It's been shown to be in academics as well, right? Sometimes you're in a class, and even though it's an easy class, it's so unmotivating that you can't even pull it together to get a good grade in it because you just don't care, you know? And then there's the classes, hopefully you don't have too many of them, that are so difficult that you're also not motivated to try to do very well. But then there are the classes that are just the right amount of stress that make you work hard, to do well, because you know you can do well at it. So that's an example. That's an example of a curvilinear relationship, right? Too little stress, you didn't do very well. Too much stress, you don't do very well. But in the middle, you do pretty well. So Pearson's R doesn't apply to something like this. And the important thing for you guys to understand when you're doing this is that, let's say you run some little study here, okay? And it's a correlational study of some kind. And you just think you're going to calculate a Pearson's R, and it'll tell you the degree of relationship. But if you haven't done a scatter plot, it could be something like this, and then your numbers will be wrong. So doing a scatter plot first is a really important, really easy way of seeing whether a Pearson's R is appropriate here. Okay. By the way, if anybody has questions, I'm kind of assuming this stuff is real straightforward, but if anybody has questions, feel free. Now, generally when we're calculating R, it's from a sample. Right? Generally, I get a correlation coefficient from a sample. But I would like to generalize to a population. There are two major problems with this, if I'm trying to go from a sample correlation to generalize to a population. One is something we call restricted or truncated range. Restricted or truncated range. Here's an example. Let's say, actually, let me draw it on this one. It would be even better. Let's say I'm interested in looking at income as a function of years of education, okay? Now, the data are pretty good that show a positive correlation for, that is, as the number of years of education increase, so does your income, until maybe about the PhD level. But that's a joke. That's a joke. Okay. All right. I have to do things, too, to keep me awake. Okay? So, but the relationship is pretty well known. That as your years of education increase, so does your income. Okay? Now, what if I restricted the range and I only looked at people who graduated college? So let's say that's in here, between these two lines. I have restricted or truncated the range. Now, look at the points in here compared to the overall points. Or let's look at the overall points first. For the whole group, what does that look like, right? This whole group, what kind of correlation does that look like? And we know it's positive, but does it look reasonably strong? If I was to draw a curve around this, does that look like a reasonably strong, yeah? Okay. Now, if I just look between those lines, what does the relationship look like? Does it look as strong as the other one? No. No. I've artificially decreased the correlation coefficient because I have restricted the range of one of the variables. Okay? So that's a restricted or a truncated range can artificially lower your correlation coefficient. The truth is, it could do all sorts of bizarre things, right? Because to go back to this curvilinear relationship again, if you haven't graphed it so you don't know it's curvilinear, all right? Depending on where I restrict the range will give me a different answer. If I restrict the range here, it's going to look positive. If I restrict the range here, it's going to look like 0. If I restrict the range there, it could look negative. You have to plot these things. Okay? So restricting the range can be a problem. What's the other problem that we have? Something called bivariate outliers. Bivariate outliers. We all know what an outlier is, right? What's an outlier? Right, it's an extreme score. So what's a bivariate outlier? It's an extreme combination. It's an extreme combination of the scores. Right? Because if I was correlating, let's say, height and weight, if I had somebody who was very tall and very heavy, that would not be so unusual. Right? But if I have somebody who's very tall and very thin, or very short and very heavy, that's an unusual combination. And what happens then? Well, let's take a look. Okay, let's go back to this correlation for a minute. Let's say I have a really unusual bivariate outlier. It's down there, let's say. What happens to my correlation? What happens then to the correlation of those points? It becomes weaker, right? Because I would have to draw the envelope all the way around, right? And that would be, it would decrease the size of the correlation. If you had an outlier out here, that would conceivably increase the size of the correlation. So that's, but it's at least in the right direction. This bivariate outlier causes you more problems. Okay? So these are the two major problems you have in going from a sample to a population. You might have a restricted range, or you might have bivariate outliers. But again, you graph these things, it's useful. You can find out what's going on. Okay, now we're up to formulas. If I had population parameters, this is what the formula would look like. Okay? Now the top, the numerator of this, is something called the covariance. The covariance. And the covariance is the degree to which the two variables vary together. The degree to which the variables vary together. So that's the numerator, the covariance. And you might hear this term like in higher level stats if you ever get there, covariance. Dividing the covariance by this product, the product of the standard deviations, keeps it kind of standardized between -1 and +1. All right. Now here is what he refers to as the unbiased covariance, or the covariance using the sample statistics. Notice the difference, the major difference. Here we have S, before we had sigma. So in the numerator, we have to divide by n-1, not n. Right? They just have to match. If you have sigma, you're dividing by n. If you have S, you're dividing by n-1. Now, what does n stand for in a correlation example? The number of pairs of scores. The number of pairs of scores. Yeah? Sure. Which way? Let's see. Okay. Play with the projector. Okay? So n is the number of pairs of scores. Okay? So let's actually do an example, right? Here's our example. The question is there a relationship between knowledge about AIDS and tolerant attitudes? Okay? So our x variable is knowledge, and y are the tolerance scores. So our question is there a relationship here? So we're going to calculate the correlation coefficient. Now, the only thing that you have not seen so far is this term, the sum of x, y. So what that is down here is another column, x, y. You take your first x score, multiply by your first y score, and that gives you your xy. And you do that for each of the scores. If you add those up, that gives you the sum of xy. Okay, that's all that is. So let's get that correlation. And you'll notice I gave you all the summary statistics. So what's n in this calculation, in this example? 10, yeah. Oh, I thought, oh, I moved it down enough so you could see the formula. It's so funny, right? Technology is supposed to make our lives better. But sometimes I just go around saying, like a chalkboard, just give me a chalkboard. I used to teach with a chalk, really. Okay, so that's our correlation, right? So first of all, what kind of correlation is it? It's positive, meaning what? Yeah, let's make it specific. Let's make it specific. On an exam, I'm going to ask you to be specific. What is a positive correlation in this context? Yeah, as knowledge is increasing, so is tolerance. Not necessarily that knowledge or education causes the tolerance, but they seem to move together. All right? Now, what about the strength of this relationship? What do we think? Yeah. It's pretty strong, right? It's pretty strong. It's close to 1. Let me give you some criteria for deciding what's a small, medium, or large correlation coefficient. The really easy numbers, 0.1, 0.3, 0.5. So 0.1 to 0.29. 0.1 to 0.29 is a small correlation. 0.3 to 0.49 is a medium correlation. And 0.5 or larger is a large correlation. Now again, that's kind of within the context of psychology, all right? If you were doing something in physics, and you were correlating actual, physical measures or forces or something, the correlations might be much higher. But when you're talking about people and things like that, we don't aim quite that high, all right? So those, and again, also understand, I gave them to you for the positive numbers. They're exactly the same for the negative in the other direction. So what do we have here? We have a large correlation. A large correlation. Okay? Any questions on this? Have you got something where it's from? Yeah?
Can you just repeat those numbers?
0.1 to 0.29. 0.3 to 0.49. And 0.5 or larger. You're welcome. And again, that applies for the negatives. Okay, what I'd like to show you is there's a couple formulas. I just want to show you. He has in the book, there's like several formulas for correlation. It's not a big deal. There's a couple things I want to point out about them. You can use whichever ones work for you. This is not going to be one of them, by the way. This is not going to be your favorite correlation. But I just want to show you something about this formula. Okay? On top, the numerator in this formula is something called the sum of products. You might see this term, the sum of products, right? It's the sum of products of the deviation scores of x and y. That's really what's going on there. So in this formula, that numerator is not the covariance. It's not the covariance. It's the sum of products. If you took the sum of products and you divided by n minus 1, that would be the covariance. So I'm bringing those things to your attention because you might see it in various places. And understand that the sum of products is like the step before you get a covariance. Okay? And again, right, it's like sum of squares before you get a variance. It's the same idea. The same idea. Okay? But again, you wouldn't use this formula because it would be so annoying. You'd have to find everybody's deviation scores, multiply. It would just be out of control. Here's a formula that I always used. He's not crazy about it. You can do whatever you want. This is called the raw score formula. And if you'll notice, it's just an expansion of the one on top. It's just easier to work with. Because sometimes you don't have the summary statistics, right? But why I'd like to point out this formula, I can tell some of my overheads are like, they're starting to like bleed, you know, because they're old. So this is the raw score formula when you just have raw scores you're trying to deal with. And so like I said, I always used it. He doesn't like this one, and for good reason. It's easier to make mistakes and harder to find them in this formula than on the one on top, the one that he uses, the one that he recommends. But I'll tell you, the one on top, the one that he recommends, this one, make sure that if you're doing it, you always carry everything to 4 decimal places, because it's subject to a lot of rounding error. So just be careful with that one. So why did I show you the bottom one? Because I want to show you the sum of products thing, right? Note, what is this one on the bottom? What does that look like? Does that structure look familiar to you? It should, from like second week of class. It's a sum of squares formula. That's the sum of squares for x. That's the sum of squares for y. That's the sum of the products. Look how the structure is the same. Except for the sum of products, we're multiplying x by y instead of x squared or y squared. I'm just trying to show you these commonalities, because if you understand the patterns that go through it, it'll be easier to remember some of this stuff. All right? So now, what if, okay, so calculating correlation coefficient, you see that's easy, you understand it, no problem. What if I wanted to test it for significance? Okay, I want to test a correlation coefficient for significance. First of all, what's the hypothesis I'm testing? The hypothesis I'm testing is this. Here's the null hypothesis. That little letter, that's the Greek letter rho. Remember, our hypotheses always have population parameters. So rho is the population correlation coefficient. The population correlation coefficient. Correlation coefficient. Okay? So it's a population correlation coefficient. So that null hypothesis is that the population correlation is 0. That is, there's no relationship between the two variables. If I reject it, then I'm left with the alternative that there is a relationship. That there is a relationship. Okay? So how do we test this? Well, there's an easy way and a hard way. The hard way is, and it's not all that hard, is to change this correlation coefficient into a t. Into a t observed, a t calculated. And then if I changed my r into a t, how would I find significance? How would I test it for significance? What would I do? I get t observed. How do you test it for significance? Next week, right? This is the t-calc. Yeah, exactly, right? You compare it to your t-critical value, right? And you find significance. That's if you transform it into a t. We have an easier way of dealing with it. Okay? Here's the easier way of finding significance. You've calculated your correlation coefficients. All we have to do is go to a handy-dandy table in the back of the book. This is table A5. And if you'll notice, across the top are our alphas, one-tailed or two-tailed. Down the side here are our degrees of freedom. In this body, these are our critical values. Our critical values. So all you have to do is look up an R critical value and compare it to the R that you calculated. That's it. That's it. So let's actually do that for this example. Okay? So what do I need to know? What do I need to know that I'm missing? I have my calculated R. That was 0.73. Degrees of freedom. Degrees of freedom for a hypothesis test are big N minus 2. Big N minus 2. Again, the number of pairs of scores. So what do we have here? How many degrees of freedom? There's 8 degrees of freedom. We'll assume alpha 0.05, two-tailed. 8 degrees of freedom. My R critical value is 0.632. Let's write that up here. Okay. What decision do I make? Right, because this is just like a regular hypothesis test, except instead of T's, now you have R. So my calculated correlation is 0.73. My critical value is 0.632. Am I rejecting or am I failing to reject? I reject. I reject the null hypothesis. And again, this would be the same in the negative direction, you know? So just think of it that way. So I'm rejecting the null hypothesis. Therefore, what? There is a relationship. There is a relationship between knowledge and tolerance, tolerant attitudes. Okay? Questions on the hypothesis testing? Yeah?
What if the R calculated was negative 0.73?
Yeah, as I said before, it's the same on the other side, right? What if it was negative 0.73? So then all we think of as the critical value is also negative, right?
Okay.
Yeah, just like with T. They don't give you the negative numbers because they're symmetrical distributions, so they don't have to. It would be like wasting another page of numbers. Yeah?
When you're doing null hypothesis testing for this,
Yeah.
Since you're doing P equals 0, aren't you just
R,
saying that
row.
Yeah, sorry. Equals
That's
0,
okay.
aren't you just
I
saying
get
that
confused
there is
easily.
some relation or some correlation, but not saying which direction it is? So
Oh, it's a non-significant thing? Yeah, you're hypothesizing that there's a relationship, but not necessarily in the direction.
then if you wanted to test a directional correlation,
Yeah.
Would you use a one-tailed test then? Or?
Yeah, you could. You could. We won't, but you could. Yeah. Yeah.
How would you like this answer in APA?
I believe you'll be doing that in lab. Yeah, I mean, it's essentially R, and in parentheses, in general, it's N, not degrees of freedom, but check that. Okay? Equals whatever it equals, P less than 0.05 two-tailed. It's the same thing. Same idea. Hang on, I saw her first, and I'll come back to you. Yeah? What do you mean? Because, right. I mean, that's just what he was asking. So what? I'm not understanding. Yeah, you could. Yeah, you could. You know, then your hypothesis would be directional, and then you would look in the 0.05 one-tailed column. Yeah, same thing. Yeah.
What exactly does the R critical value signify? Like if we had found an R of 0.6, it would still be a fairly strong correlation, but it would fail to reject.
Yeah.
So what does that mean?
Yeah. Okay, we're going to get into that momentarily, right? Because the point is here, and we can actually go back to this, right? It could be a fairly strong correlation, but if it's not significant, that means that you can't say that your results were not due to chance, right? In some ways, R is actually more like effect size than significance, but look, okay? Let's talk about our sample size and what was going on here, right? For a sample size of 10, meaning degrees of freedom of 8, the critical value we needed to beat was 0.632. That's high. That's very high. Why? Because your sample size was small. Your sample size was small. Now, what happens as your sample size gets bigger? Let's take it back a step. What happens to T when your sample size increases? Anybody remember this? You need to remember this. What happens to T as your sample size increases? What happens to your standard error when N increases? Decreases. You all know that, right? It decreases. What happens as your standard error decreases? What happens to T? It increases, right? The denominator goes down, t goes up. So as n increases, your t gets bigger. That is not what happens with r. That is not what happens with r. With r, as you increase your sample size, it just gets to be more like the population correlation. R becomes more like rho. So it could be small, it could be big. It just reflects the population more closely or more accurately. Are you understanding when I say that? I'm not sure. Like, I know people are writing things down, but I want you to get the idea behind it. Okay? It's like does anybody here do any gambling? Okay. Oh, no. Sometimes people admit to that. If you go to a casino, in which scenario are you more likely to lose money? If you play for 15 minutes or for 3 hours? 3 hours, why? Yeah, but why? Yeah. Exactly, okay? The odds are always in favor of the house. It wouldn't be a business if it wasn't always in their favor, right? So the longer you play, the closer your proportions will come to reflecting reality, which is in favor of the house. Okay? Understand that. It's like if I flip a coin 10 times, am I going to get half tails and half heads always? No. But if I flip it 10,000 times, then the proportion will be 0.5, very, very closely. Because the larger sample size, the closer you get to the actual reality. All right? So it's the same thing here. The larger your sample size, the closer R will come to rho. Okay? All right. So I don't know if that actually answers your question in as much detail as you had in mind, but sort of, right? Enough? Yeah? Okay. All right. So now here's a question. Degrees of freedom. Degrees of freedom. All right? Why are they n minus 2? Well, think of it this way. Here's the simple way to think about it. If I have 2 pairs of scores, right? I only have 2 people and I get 2 pairs of scores. Let's say here and let's say there. What's the correlation? Yeah, right? You know this. The correlation between these two is 1. It's a perfect correlation. Why? A line is defined by 2 points, right? So if you have 2 pairs of scores, you know nothing about the actual correlation. So we take off those 2 scores as the degrees of freedom. The truth is, right, so that's an inflated correlation, right, because it's telling you it's 1 when really we have no idea what it is. The truth is, it's still inflated even as you increase your n, even to about 10 is still an inflated correlation coefficient. So you really have to have a reasonable sample size when you're doing this. Okay? All right. Now assumptions. Let's talk about the assumptions if you're doing hypothesis testing, right? Every time we have a hypothesis test, we have to talk about our assumptions. Okay. First one, independent random sampling. You've seen this before. But in this case, the independence means between the pairs of scores. Between the pairs of scores. It can't be between individual scores because usually one person is giving you both scores. So those aren't going to be independent. But there needs to be independence between pairs of scores. Okay? A normal distribution, that both variables are normally distributed. Both variables are normally distributed. Also, that the variables should be interval or ratio level. Interval or ratio level. Okay? And what happens when they're not, we'll talk about in a minute. Now, this last assumption is a stricter assumption. That's called that both variables should create what's called a bivariate normal distribution, meaning if I plot one variable on the x-axis and one variable on the y-axis, I need to show the probability of those combinations. How do I do that? In a third dimension. That's the next page. That's this picture. Okay? If this is my x and this is my y, so probability has to be shown in a third dimension. So it gets this kind of hat-like shape because you're plotting the pairs of scores. All right? This would be a bivariate normal distribution. So in theory, your variables have to meet this assumption. If you have a curvilinear data structure, they won't meet this assumption. They won't meet, this will violate the bivariate normal distribution. Okay? So what do? If your bivariate distribution is really strange, it's not normal, or if your variables are not interval or ratio level, let's say they're ordinal level, here's what you can do. You can take your scores and you can rank them. Rank them. First, second, third, fourth, fifth. You just rank them. You rank both sets of scores. And then you take the ranks and you throw them into a Pearson formula. That gives you a correlation coefficient called Spearman's R. Spearman's R. So it's a little R sub S. Spearman's correlation coefficient. Just taking ranks and throwing them into a Pearson formula. Right? We're not going to do any computations like that. This is typically, I mean, it's really funny. I've taught this in every other undergraduate class I've ever taught, but he doesn't go into it in great detail. I don't see a particular reason to. But if you come across it, it's great because then it's the same formula, but you're just using ranks instead of the raw scores. Okay. And now let's just talk a bit about the uses of Pearson's R. Some of it is obvious, but I'm going to talk about a couple of uses that are not so obvious. Okay? Let's talk about reliability and validity. What does reliability mean? If a measure is reliable, what does it mean? Reliability. Yeah. Exactly, right. You test something over again, you're likely to get the same results. So there's different types of reliability, all right? One, the first one is like what we're talking about is test-retest reliability. Meaning, let's say you're measuring something stable, okay? Let's say IQ in adults, all right? We'll assume that that's reasonably stable. That means that if I measure you now and I measure you in 6 months, in theory, I should get similar scores. How would I know? I take the scores from now and I take the scores from 6 months and I calculate a correlation between the two. If I do that, the correlation should be very high. Very high. Not 0.5 high, but like 0.9 high. Okay? That's test-retest reliability. What other kinds of reliability are there? Something called split-half reliability. That's, you take a test and you divide it, because you want to see the internal consistency of the test. So you take the even numbers, the scores for the even numbers and the scores for the odd numbers, and you calculate a correlation between the two of those. Those should also be the same. Right? It should be a high correlation. Now, there are actually other measures to do it that are more sophisticated than that, but you could do that. It's a very simple way of looking at it. So that's split-half reliability. Yeah? Split-half reliability is you're looking at a test to see if there's internal consistency. So you take everybody's scores for the even numbers and everybody's scores for the odd numbers of questions, and you calculate a correlation between those. Okay? And then the last kind of reliability, inter-rater reliability. That's when more than one person is examining something and you calculate correlations between those. For example, I worked in baby testing, right? And in baby testing, sometimes you're watching a baby's behavior. You know, you're watching, are they looking here, are they looking here, are they looking here, are they looking here? So I could score a baby's looking pattern But then someone else should also be scoring the baby's looking pattern. Either they're also looking at the same time, or sometimes the session is recorded and then somebody scores it offline. The correlations should be very high, because if they're not, that means that the two of you are seeing different things, which is not good. Not good, right? So for example, if you're looking at toddlers, and one judge or rater is seeing a toddler pat another toddler and saying, oh, he's showing a sign of affection, and another rater is looking at saying, no, he's smacking him around, that's a sign of aggression. They're looking at different things. So again, the correlations should be high. They should be high. Okay? So those are our measures. And it's also important to make sure that you're not the only one seeing what you think you're seeing. Okay? So those are 3 measures of reliability. Validity. What does validity mean? If a measure is valid, in particular we'll talk about criterion validity of a self-report measure, but what does validity mean? Anybody know that term? Validity? Yeah.
If your results actually relate to what you're trying to find?
If your thing measures what it says it's measuring. Right? Like, is IQ measuring intelligence? Well, it depends what intelligence is. But so, for example, criterion validity of a self-report measure. Let's say I'm interested in developing a measure of aggression. So I give people, this self-report measure, and they rate how aggressive they are under various scenarios. Okay? And then I follow them around. They don't know I'm following them around, but I follow them around, and I see how they actually behave. Are they picking fights in a bar? Are they pushing people out of the subway car? What are they doing? I could calculate a correlation between those 2 measures, and then I would know if my self-report measure actually measures aggression. Okay? So those are 3 interesting ways that correlation is used, aside from the ways that we've been talking about. Yeah?
So it's self-report of a subject versus what the experiment.
What you actually see. Yeah. Because again, it's validity. You want to know, is it measuring what it's supposed to be measuring? So if you go out and you say, well, these are acts of aggression, how does the person view those acts? Okay. And that's like aggression. It could be shyness. It could be, there's all sorts of things it could be. All right? And then the rest of this stuff is just kind of whatever, right? Measure the degree of association between 2 variables that are not previously related but are predicted by some theory. For example, the original, and I think I mentioned this before, the original research on smoking and cancer was all correlational. We just saw that people who smoked tended to get cancer. That was correlational work, but it informed future research, right? So very often you start out looking at that, and then you try to take the research into a different realm in order to establish causality. Okay? And so this is just more stuff that I don't think is any big deal. Okay, questions on that? Questions on that? All right, here's one last cartoon, okay? So you guys can wake up. I like this. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. I like this little series. It's very cute. All right, folks, that's it. We're not starting regression today. Good luck. I'll see you on Monday.